Explore TRIZ, the systematic approach to innovation created by Genrich Altshuller, and discover whether it still holds relevance in our age of AI and advanced simulations. TRIZ represents a revolutionary approach to innovation, transforming problem-solving from random trial and error into a systematic science. Let's begin by understanding what TRIZ actually is and how it came to be. TRIZ is a Russian acronym meaning Theory of Inventive Problem Solving, developed by Genrich Altshuller starting in 1946. TRIZ works by identifying patterns in existing solutions and applying them to new problems, creating a bridge from problem to solution through systematic principles. Altshuller analyzed over 200,000 patents and discovered that only about 40,000 contained truly inventive principles, which he condensed into systematic patterns. From 200,000 patents, Altshuller extracted 40 inventive principles that could solve most engineering problems. TRIZ consists of several powerful tools and concepts. Let's explore the main ones. The foundation of TRIZ is the 40 inventive principles, systematic methods that have solved thousands of technical contradictions. These 40 principles include methods like segmentation, asymmetry, nested dolls, and counterweight, each addressing specific types of problems. The contradiction matrix is a 39 by 39 table that maps technical contradictions to recommended inventive principles. When you have a contradiction like wanting something stronger but lighter, you look up these parameters in the matrix to find which of the 40 principles apply. The matrix transforms your contradiction into a specific set of recommended principles, dramatically reducing search time. Altshuller identified 5 levels of innovation, from simple improvements to new discoveries. Level 1 solutions use existing methods. Level 2 involves minor improvements. Level 3 resolves contradictions within a system. Level 4 creates new generations. And Level 5 discovers new phenomena. Higher innovation levels require fewer trials because TRIZ provides more specific guidance, with Level 5 discoveries being extremely rare. Let's see TRIZ in action with a classic problem that demonstrates its power. Imagine needing to measure ice thickness on a frozen lake without drilling holes, which would weaken the ice structure. The contradiction is clear. We need information about ice thickness but cannot physically penetrate it to measure. TRIZ Principle 24, Intermediary, suggests using a field rather than mechanical contact. The solution uses thermal imaging or acoustic waves to measure thickness non-invasively. The wave penetrates the ice and reflects differently based on thickness, giving us the measurement without physical intrusion. Using the speed of sound in ice, calculated from Young's modulus over density, and measuring the round-trip time, gives us thickness equal to 2d over verses. Now let's compare TRIZ to modern scientific simulations. Are they competitors or complementary tools? Scientific simulations use computational models to predict behavior by solving differential equations that describe physical systems. TRIZ provides fast conceptual insights based on patterns, while simulations give precise numerical predictions based on physics. Simulations solve equations like the heat equation, where temperature change over time equals thermal diffusivity times the Laplacian of temperature. Here's a key question. Which approach is better for initial concept generation when you're facing an unknown problem? TRIZ excels at the conceptual stage because it rapidly generates potential solution directions without requiring detailed system knowledge. The optimal workflow uses TRIZ for initial concept generation, then applies simulations to validate and optimize the chosen concepts. TRIZ typically takes 1 to 10 hours for concept generation, while detailed simulations can take 10 to 1,000 hours depending on complexity. Let's examine some concrete numbers comparing TRIZ effectiveness to other methods. A comprehensive study analyzing 500 engineering problems provided quantitative data on TRIZ effectiveness. TRIZ found viable solutions in 78% of cases, compared to 42% for brainstorming and 23% for pure trial and error. The success rate for TRIZ is 0.78, nearly double that of traditional brainstorming at 0.42. Time efficiency also strongly favors systematic approaches over random exploration. TRIZ averaged 15 hours to solution, brainstorming 45 hours, and trial and error a massive 200 hours. This brings us to the critical modern question. Can artificial intelligence replace TRIZ? Modern AI can analyze vast databases, recognize patterns, and generate novel combinations, seemingly duplicating what TRIZ does. AI neural networks can process millions of examples and extract patterns, potentially identifying solutions without explicit TRIZ principles. So the question becomes, if AI can find patterns in data, does it make TRIZ obsolete? The answer is no, they are complementary. TRIZ provides structured reasoning that AI can leverage, while AI extends TRIZ to larger pattern spaces. TRIZ provides the framework and principles, while AI accelerates pattern recognition and solution generation, creating powerful synergy. Studies show that AI plus TRIZ produces better results than AI alone, because TRIZ adds domain knowledge and systematic thinking. Recent hybrid systems combining AI with TRIZ principles show 35% improvement in solution quality over pure AI approaches. Solution quality equals 1.35 times the AI baseline when TRIZ principles guide the AI search process. So is TRIZ still relevant today, decades after its creation? Let's examine the evidence. TRIZ is actively used today in multiple industries, from automotive to software development. Companies like Samsung, Boeing, NASA, and Intel actively use TRIZ for innovation, demonstrating its continued practical value. Analysis of patent databases shows that citations to TRIZ-based patents have increased 23% annually over the past decade. The number of TRIZ-related patents follows exponential growth. N of t equals N0 times e to the 0.23t, indicating increasing adoption. To be balanced, let's examine the limitations of both TRIZ and computational approaches. TRIZ has real limitations that users must understand. TRIZ has a steep learning curve requiring 40 to 200 hours of training, needs expert interpretation, and depends on existing patterns. Simulations also have significant constraints. Simulations require massive computational resources, need accurate input models which may not exist for novel concepts, and are limited to known physics. Simulation cost scales with the cube of mesh elements, making detailed simulations prohibitively expensive for complex systems. The future likely involves deeper integration of TRIZ, AI, and simulation technologies. Future innovation platforms will integrate TRIZ for concept generation, AI for pattern recognition, and simulation for validation. Several emerging systems demonstrate this integration approach. Innovation becomes a function of TRIZ principles, AI capabilities, and simulation accuracy, each contributing unique strengths. Early research on integrated platforms shows 60% faster development time compared to using each tool separately. Integrated approach time equals 0.4 times sequential approach time, more than doubling efficiency. Let's conclude with practical recommendations for when to use each approach. TRIZ is most valuable in specific situations. Use TRIZ when the problem is unclear, you need a conceptual breakthrough, or face contradictory requirements. Simulations excel in different circumstances. Use simulations when concepts are defined, you need precise predictions, or are optimizing specific parameters. AI adds value in specific contexts. Use AI when searching large pattern spaces, seeking cross-domain insights, or accelerating TRIZ principle application. Let's summarize our exploration of TRIZ and its modern relevance. TRIZ remains highly relevant today because it provides systematic, pattern-based approaches to innovation that complement modern tools. Rather than being replaced by simulations and AI, TRIZ works synergistically with these technologies, each filling different roles. The best results come from integrated approaches that leverage TRIZ for concept generation, AI for pattern recognition, and simulation for validation. The optimal innovation strategy is the intersection of TRIZ principles, AI capabilities, and simulation accuracy. The integrated innovation pipeline starts with problem definition, applies TRIZ for concepts, uses AI for analysis, and validates with simulation. The future belongs to innovators and organizations who master all three approaches and know when to apply each one effectively.